Okay. Nice. Wait, I can actually turn this up. Does that turn up the gain? Test. Oh, test, test. All right, nice. Okay, so that's the first route. It's just form a carboxylate somehow. Esters can also be synthesized by an acid catalyzed nucleophilic carboxylic acid with alcohol. Okay, yeah. So what they're saying is it's a mixture of cost and solubility. But actually, there's no water, so it just has to be liquid. That's actually that's good. Mechanism of Fischer esterification is shown. Carboxylic acids are not reactive enough to undergo nucleophilic addition directly, but their reactivity is greatly enhanced in the presence of a strong acid like sulfuric or hydrochloric. The mineral acid protonates the carbonyl group oxygen atom, thereby giving the carboxylic acid a positive charge and rendering it much more reactive to its nucleophiles. Yeah, so this carbon is very electropositive. Subsequent loss of water from the tetrahedral intermediate yields the ester. Alright, let's go through this. Okay, so the first thing that happens is this carbonyl takes a proton, and we get okay, now we've freed up this carbonyl so that ROH can come in with its oxygen and attack the carbonyl carbon and push a lone pair onto the newly protonated carbonyl. Now we get this like geminal diol thing. Uh, a geminal diol tetrahedral intermediate. Transfer of a proton from one oxygen atom to another yields a second tetrahedral intermediate and converts the OH group into a good leaving group. Oh wait, no, wait. See, that's kind of the weird part about this mechanism, right? Is like it does seem extremely reversible. Because why wouldn't you take if you're water and you were like, okay, I want to take a proton. Why wouldn't you take the acidic proton? But the point is, this mechanism is just what examples of things that could happen. So it's not that it takes this proton; it's that it takes the other proton, which dumps this and then kicks water. So this is actually going to be gone. This is a carbonyl. So now we have our ester. So my questions about is how does the proton transfer happen? And why doesn't, let's see, this is step 1, 2, 3. The net effect of Fischer esterification is substitution of a hydroxy group by a alkoxy group. All steps are reversible, and the reaction typically has an equilibrium constant close to 1. Thus, the reaction can be driven in either direction by a choice of reaction conditions. Ester formation is favored when a large excess of alcohol is used as solvent, but carboxylic acid formation is favored when a large excess of water is present. So if you have an ester in acid and you want the carboxylic acid, you just add a lot of water. How do we prepare this? Well, we would clearly start with propanol, yeah, and then, yeah, with a Alright, so here we're going to start with acetic acid. So this one's easy. Alright, here we have, so we'd start with butanoic, methanol, and acid. Here we'd start with, it's got a weird name. It's going to be cyclopentanol carboxylic acid. And isobutanol, or no, wait, isopropanol. Or wait, I think you just call it 2-propanol. So it's going to be psych, pent, Ca, then 2-propanol. And then acid. The following molecule is treated with acid catalyst, an intramolecular esterification product occurs. Ooh. Wait, I actually want to draw this one out. This one seems sick. So if we go here. Oh wait, this is OH. So okay, let's recall what the mechanism is. So this gets, the first step is that acid protonates the carbonyl. Then alcohol attacks. I don't know how to name these heterocycles. Oh, let's go. That's exactly what I wanted. That's what I got. Yeah. Yeah, the intramolecular stuff is always so interesting. All right. So now we want to make amides. So amides is important because I don't know. I think it's like biologically relevant. Amides are difficult to prepare by direct reaction of CAs with amines because amines are bases that convert acidic carbonyl groups. Um, because amines are bases that convert acidic carboxyl groups into their unreactive carboxylate anions. Right. Okay, that makes sense. Yeah. Thus, the OH must be replaced by a better non-acidic leaving group to carry out a nucleophilic acyl substitution. In practice, amides are often prepared by activating Ca with carbodiamide, followed by addition of the amine. Dicyclohexyl carbodiamide, DCC, and something else. We only really focus on DCC. Are commonly used. As shown in the figure, the acid first adds to a C double N bond, then substitution by the amine. Alternatively, and depending on the reaction solvent, the reactive acyl intermediate might also react with a second equivalent carboxylic to generate an acid anhydride that then reacts with the amine. The product of okay, that's interesting, I guess. All right, so we'll try to go over this a few times. So first, a nitrogen picks up a proton from the carboxylic acid. Then now we have a carboxylate. And the carboxylate then attacks the carbon. Then nucleophilic attack by the amine onto the carbonyl carbon. Forms an anion. The anion then regenerates the carbonyl. Forming a carbonyl actually on the leaving group too. Oh yeah, dicyclohexyl urea. Mm. I see. Okay, so I finally get what this is saying. So if we disable one amino acid's OH group and we disable the other acid's amino group, then we can do this DCC thing and we can do the same exact mechanism we already saw and get a dipeptide. Okay. So all right. So to convert a carboxylic acid into alcohols, we said in chapter 17 that carboxylic acids are reduced by LAH to give primary alcohols. But we defer to discussion of the reaction mechanism. Okay. In fact, the reduction is a nucleophilic acyl substitution reaction, which H replaces OH to give an aldehyde that is further reduced by addition again to produce a primary alcohol. This is a lot like well, it reminds me of the triphenylmethanol synthesis, in which two nucleophilic acyl substitution substitution reactions happen. But actually, wait, this is first one substitution. The second one is addition. So there's actually a difference. Yeah, and then you add acid. Okay. So you have to add acid though. Oh, interesting. Oh, it's a geminal dianion. It's not like what was that we saw yesterday where there was actually a 2 plus charge or a 2 minus charge on something. Direct conversion of carboxylic acid to an acyl derivative by nucleophilic acyl substitution does not occur in biological chemistry. As in the laboratory, the acid must first be activated by converting the OH into a better leaving group. This activation is often accomplished in living organisms by reaction of the acid with adenosine triphosphate, give an acyl adenosyl phosphate or an acyl adenolate. Mixed anhydride Oh yeah, that's actually cool. It's like there's two nucleophilic acyl substitutions, but it's like yeah, okay. Okay, this is the good one. All right, so chemistry of acid halides. All right, so first off, how do you prepare them? You have thionyl chloride, and you have phosphorus tribromide. So you can get acid chlorides and acid bromides. I don't know I know the mechanism for this, but I don't know the mechanism for this. Presumably, let's see what happens. So in this one, I already forgot. Oh, there's a lot of mechanisms to remember. Let me think about it. Okay, yes. So it's okay. So the hydroxyl oxygen lone pair dumps into a pi, which forces the oxygen pi lone pair onto a attack to sulfur, which forms an anion. The anion drops down, kicks off chlorine. Chlorine now is or it's actually a chloride. The chloride ion is now a nucleophile, which then attacks the carbonyl. Which then removes the good leaving group of the sulfur compound. And there's a special name for it, but I don't remember it. So presumably this PBr3 thing, a very similar thing happens, is that this lone pair comes here, this attacks the phosphorus. Oh, but there's no oxygen here, so I don't really know what happens there. Let's see. These are alcohols, but what about carboxylic acid? I think it's this. So I want to know about. Oh, I need to do this one too. Dibol. This probably has PBr3 in it. Okay, I guess I don't have it. But it's fine. It's fine. Um, all right, acid halides are among the most reactive carboxylic acid derivatives and can be converted into many other kinds of compounds by nucleophilic acyl substitution mechanisms. The halogen can be replaced by OH to yield an acid, OCOR to yield an anhydride, OR to yield an ester, NH to yield an amide, or by R prime to yield a ketone. Right, to get the R prime, this is the one that I messed up on in the homework. It's what was it? Actually, no, I think I like literally just don't know how to do it. Okay. Oh yeah, see, I don't know how to do this. I don't know what this is about. R prime 2 copper lithium. We will learn about that. Okay, here we go. So this is the easy one. So conversion of acid halides into carboxylic acids by hydrolysis. Acid chlorides react with water to yield carboxylic acids. This hydrolysis reaction is a typical nucleophilic acyl substitution is initiated by attack of water on the acid chloride. Tetrahedral intermediate undergoes elimination of Cl- and loss of H+. Okay, so that's like super easy. Alright, so let's just do hydrolysis of acid chloride. So we have a OCl. Then we have H2O. Tax this. Because HCl is formed during the hydrolysis, the reaction is often carried out in the presence of a base. Okay. All right, cool. All right, anhydride formation from acid halides. Nucleophilic acyl substitution reaction of an acid chloride with a carboxylate anion gives an acid anhydride. Both symmetrical and unsymmetrical acid anhydrides can be prepared. All right, so we start with something like sodium formate and acetyl chloride. But this is where I forgot about the naming of acid chlorides. So it would be like benzoyl chloride or something like that. Okay, and what happens is presumably this goes in here, pops it up, pops it off, kicks it out. They're pretty low yield actually. Okay, esters. Ooh, look at that. That looks good. Acid chlorides react with alcohols to yield. Yeah, oh yeah. I mean, this is like the same thing as water. This is the most common way to prepare esters in the lab. As with hydrolysis, alcolysis reactions are usually carried out in the presence of purity in NaOH to react with the HCl formed. Okay, so the reaction of an alcohol with an acid chloride is strongly affected by steric hindrance. Bulky groups on either partner slow down the reaction considerably. Yeah, but look at this. Secondary alcohol, bulky substituent, still 97%. Oh, okay. Yeah. So, yeah, so secondary alcohol. Okay. Let's see. How would we prepare the following esters? Okay, so this would be called but. Wait, no, wait, hold on. Oh, oh, yeah. For a second, I was like triple. So this would be called methyl. So to name an ester, it would be propanoic acid. So then it would be methyl propanoate. So this is methyl propanoate. And what we want to do is we want to form this. So specifically with an acid chloride, well, then we're going to start with, obviously, propanoyl. It's probably propanyl. I don't know why they don't just standardize it, man. It's like, you have to remember which one's an ill and which one's an oil. But I think it's ill. So propanyl chloride. Let's try it out. Then we're going to react this with an alcohol, which is going to be methanol. Is that all we need? We literally just need the two things together and that's it? I think that's true. Okay, so then B, we have C, O, O, C, O, C. So this is going to be ethyl acetate, or my preferred ethyl ethanoate. And I bet if you look that up, you actually get something. Because ethyl ethanoate. Okay, now here we want to form ethyl benzoate. So first we start with benzoic acid. And then we just turn this into an ethyl. So we're going to start with benzoic acid. Or no, wait, we're going to start with benzoyl chloride. Okay, so then benzoyl chloride reacted with ethanol. So here, wait, I didn't actually do B. B, we start with acetic acid. Or no. We start with acetyl chloride. And then we react that with ethanol. Then here, it's just benzoyl chloride and ethanol. Which method would you choose if you wanted to prepare cyclohexyl benzoate? Wait, cyclohexyl benzoate. They didn't say anything about sterics in the fissure, but the tetrahedral intermediate, I don't know, that geminal diol intermediate seems like it would also have the same sterics. But let me just draw it out. So first off, cyclohexyl benzoate. So let's just draw benzoic acid. And now, since it's benzoate, it's going to be an ester, so then we can just draw. Okay, so that's cyclohexyl benzoate. And didn't they literally show this though? In this case, they literally show the synthesis with an acid chloride. So I guess let me just look at the answer. Oh yeah, I forgot the pyridine. Propanoyl chloride, methanol, pyridine. Acetyl chloride, ethanol, pyridine. Benzoyl chloride, ethanol, pyridine. Explaining the text, only simple low boiling. Oh yeah, that's right. But is it solid? Okay, cool. Alright, the conversion of acid halides into amides by aminolysis. Acid chlorides react rapidly with ammonia and amines to give amides. As with the acid chloride plus alcohol method for preparing esters, this reaction of acid chlorides with amines is the most commonly used laboratory method for preparing amides. Both monosubstituted and disubstituted amines can be used, but not trisubstituted. Right, oh, I forgot about this two equivalence thing. This is important. NN-dimethylbenzamide. Amide. Because HCl is formed during the reaction, two equivalents of the amine must be used. One equivalent reacts with the acid chloride and one equivalent reacts with the HCl byproduct to form an ammonium chloride salt. If, however, the amine component is valuable, amide synthesis is often carried out using one equivalent of the amine plus the equivalent of an inexpensive base. For example, the sedative trimetazine is prepared commercially by reaction of 3,4,5 trimethylbenzoyl chloride with the amine morpholine. Oh wait, this is trimethoxy. They must have to. Oh wait, no. Oh yeah, trimethoxy. Okay. Pretty interesting. Synthesizing an amide from an acid chloride. How might you prepare N-methylpropanamide? Okay, wait. So I would assume you start with propanyl chloride and you react it with methylamine. The nice thing about starting with acid chloride is you don't need that DCC stuff. Actually, how expensive is that DCC stuff? Let's find that out. All right, let me see if I can even remember the name. The internet's so bad here. Oh yeah, we need two equivalents of methylamine. Write the mechanism of the reaction just shown between 3,4,5-trimethoxybenzoyl chloride. And ooh, okay, let's do it. This sounds fun actually. But I'm just gonna write the generic. I'm not gonna write the whole thing. So 2111. So we have ROCl. So there's our acid chloride, and then we have, and I'll draw this one. So we have H, N, and it's a six-membered ring. So the first step, I think, is just nucleophilic attack. So we still have a lone pair on nitrogen. So it does this. Then we have this HCl, and the HCl reacts with another equivalent of wait, NaCl. Oh, it's because NaOH does it. Yeah, so in that case, if we had NaOH, then yeah, this goes here, this goes here. So we actually get and water, right? We also get water. How would you prepare the following amides using acid chloride and an amine or ammonia? I hate when they write it like that. It's so much harder to understand. C, 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 O, N, C. Okay, so first off, what is this called? This is going to be called N-methyl propanamide. And to form it, we'd start with propanyl chloride and 2 equivalents of methylamine. Okay, now we have NN diet benzamide. So this one's pretty easy too. So we start with benzoic acid and then take N. Okay, so we have the NN diethyl benzamide. And we would just form it from benzoic acid or benzoyl chloride and diethylamine. Okay, last one, propanamide. So wait, propanamide. That's just that's just propanol chloride and ammonia. Yo, what's up?